Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm your host, Kristin Malavenda, Communications Director for the school. In this episode, we're joined by Shreyas Sundaram, the Marie Gordon Professor of Electrical and Computer Engineering here at Purdue. And Shreyas' research is all about understanding and improving the complex networks that keep our world connected, whether it's the internet, social networks, power grids, or even robotic swarms. Today he'll explain why keeping these networks secure and resilient matters to us all. He'll also share insights about his role with Purdue's AI racing team, where autonomous Indy race cars speed around professional tracks at more than 150 miles per hour. Shreyas, thanks so much for joining me today.
It's great to be here, Kristin.
So let's start at the beginning. Tell us a little bit about yourself, where you grew up, and how you got interested and on this path to engineering.
Yeah, I was born in India, so I lived there until I was 10, and then my family and I moved to Canada, so I lived there, pretty much grew up there. I was always interested in math and science. Those are the courses that I had an affinity towards. In school, I, of course, enjoyed everything, but those are the things that I, really enjoyed doing in my spare time as well. So I'd be looking at books in the library and stuff like that. And I remember my sister asking, why is he reading those kinds of books? And my mom saying, let him be.
Let him do him.
So in high school, then I started getting exposed to programming, and I enjoyed that quite a bit. It was just really cool to be able to program stuff and see it, especially draw things on the screen, computer graphics and all that other stuff. So I knew I wanted to go into the computer discipline in some way. I was debating between computer science and computer engineering. Decided to go the engineering route just because I felt like it would give me an opportunity to explore a variety of different possibilities, not just programming, but a variety of things related to computers. And then so I did that at the University of Waterloo in Canada. That was my undergraduate institution. The curriculum there, they have an EC program just like we do here at Purdue. And there's a control systems course that's mandatory if you're a computer engineering or an electrical engineer. So I didn't know what control systems was until I took that course. And then I took it and I said, wait a minute, this is super awesome stuff. So then I said I'd love to be able to work on this, because as we'll talk about maybe a little bit later, controls has applicability to a huge variety of things. And typically controls is in the electrical engineering, subdiscipline. So then when I decided to apply for graduate school, which I did at the University of Illinois, I specified control systems as my main area of focus, and that's what took me into the electrical engineering discipline. And, fast forward several years, and here I am, a controls engineer teaching at Purdue.
How long have you been at Purdue?
10 years now.
Okay.
Yeah, so I graduated from Illinois, then I spent a little bit of time at the University of Pennsylvania as a postdoc, went back to Canada to be a professor there for a bit, and then moved to Purdue in 2015. My wife's a professor here as well.
Oh, what is she a professor in?
In mechanical engineering.
Oh, look
also
at you.
Control systems.
Look at your engineers and family.
Yep.
So
we both like to be in control. So
well, is that work at home, or is it a fight over who's in control?
We get along.
So you describe your research at being at the intersection of network science, control, communications, and distributed algorithms. Yeah. Can you break that down to what that means in everyday language?
That's a lot. Yeah, so I think it makes sense to maybe talk about each of those things individually. So maybe we can start with controls, right? So what is controls? Now, if I say the word control system to people, they might think of certain things. Typical thing they might think about is their cruise control system in their car, right? That's got the word control system in there. So what is a control system? So generally speaking, a control system is a system that makes another system behave the way you want it to. Okay. So if we think about a cruise control system in the car, the system that you want to control is the car. The behavior you want out of the car is to go at a certain speed. So the control system's job is to make that system, the car, have that behavior, follow that speed. So how does that do it? Well, the speedometer on the car sees what speed it's currently going at. It looks at the speed you want it to go at, and if it's less than that, it applies the throttle, speeds you up. If it's more than that, it either applies the brakes if you're way too far ahead of it, or just lets you slow down. So that's an example of a feedback loop, right? So essentially, there's a system. There's some desired behavior. There's sensors that see how that system's behaving. They compare it to what you want it to do. And there's a controller that says, hey, if I do this, I'm going to get it closer to the desired behavior. Gotcha. So that's basically at the core a control system, right? And controls is everywhere. You can think about the human body as a giant control system, right? It's constantly regulating the temperature, or the cells inside your body are fighting to make sure that the balance between various things is correct. Another example I do in class when I teach the undergraduate control systems class here at Purdue is the example of balancing a stick vertically in the palm of your hand,
Okay.
right? So what's the system in that case? That's the stick. What's the behavior you want? You want it to stay up. What's the sensor? The eyes, right? We're
Yep.
looking at the system and we're saying, how is it deviating? The brain is the controller, because then it says, okay, the sensors, the eyes told me the system's not doing what it's supposed to do.
Gotcha.
And I know, it's not that my brain sits there and writes down the physics for the system, but through experience and, living life, you kind of have a sense that, if I now move my hand a certain way, at a certain speed, that stick's going to react a certain way.
Right.
So the brain sends the appropriate signal to your hand, which is what's called the actuator in this case, which then applies the appropriate control inputs to the system to make it behave appropriately.
Gotcha.
And you can imagine if your brain wasn't acting properly and it caused you to jerk too much, that stick's going to fall over.
Right.
So you got to make sure that you're applying the correct control input to the system. If that stick was a lot heavier, you would have to move your hand more. If it was a very light stick, you'd have to move it a little bit less. So that's where the mathematics comes in. So controls is a very mathematical discipline. You basically say, let me first model the system. And this is the classical way to look at controls, right? Write down the physics for that. Then understand how that system will react mathematically to certain kinds of inputs. Then I can choose what inputs to apply to get the desired behavior.
Gotcha.
Another example is going in an airplane, right? Imagine you're going from 10,000 feet to 30,000 feet. There are many ways you can get that airplane to go up to 30,000 feet. One might be shoot up and then you sort of oscillate around 30,000 feet. Nobody on that plane is going to fly that aircraft ever again. However, if you're a fighter pilot and you're trying desperately to get away from something that's happening on the ground, it doesn't matter if you're going to use your air sickness bag up there, as long as you're safe. So understanding sort of the requirements for what the system should look like in terms of its behavior, that's super important. That helps guide, the design of the controllers. So that was just controls.
Yep.
Communications, obviously, is how do you get different things to send information to each other.
Okay.
Right? And so that's important, and as we'll talk about in a second, of different applications, because it's often the case that many of these control systems are operating on different systems and they're interacting with each other in certain ways. Okay, so an example of that might be something like the power grid, right? So you've got all these generators and loads and all sorts of things all over the grid. They're all trying to balance what they're doing locally, so they have local control systems to do that. But then they may also need to coordinate with each other, right? If two generators need to ramp up at the same time in order to provide, some capabilities, they may have to say, hey, are you going to give this much and I'll give this much, etc.
Yeah.
How do you do that? You have to have communications between them. So now when we think about coordinating entities, you also have to think about, if you have many coordinating entities, what does the communication patterns between them look like?
Okay.
And so that's, to capture that, you use something called graph theory. So essentially graphs are these circles, right, representing whatever it is you're modeling, people or sensors or computers or generators, and then lines between nodes indicating that they can talk to each other. But then the way the entire graph looks, the entire network looks, is very important for how the system functions. Imagine, for example, you had a big network where there was a single entity that was connected to everybody else, and everybody had to go through that entity to send information to anybody else. If that single entity failed, the entire network's in trouble, right? Because there's a single point of failure. So the field of network science basically tries to understand, how do we think about these very big networks and model them mathematically and try and understand properties of what makes certain networks strong, what makes certain networks weak. So that's network science.
Okay.
Now the distributed algorithm side of things says, okay, great. You've got control systems that are able to regulate things locally. You've got them able to talk to each other. You have a sense for what the entire network looks like. But so what? You can send me information. What am I supposed to do with it?
Okay.
So the distributed algorithms are basically what tell the individual control systems what to do with the information they get from
Makes
others
sense,
in order to get everybody to work together.
Makes sense.
Yeah, so like robotic swarms is a perfect example, right? So imagine in this case, the nodes are the robots.
Okay.
This could be drones or ground vehicles, could be heterogeneous. So imagine you've got a swarm of millions potentially, right? In the future, that's what we're thinking about these things. And they're off to go do something like search and rescue in a disaster zone. So you've got a forest fire, you've got an earthquake, something that bad's happened. You want to go search for survivors. Now it's a big area, it's challenging to search. So you've got, these large teams of robots, they got to work together to say, you guys go over here, you guys go over here. If you see something, call the supply robots over. So in that case, what needs to happen? They need to be able to talk to each other.
Yep.
There's a certain network that forms based on that. And then if I want to do something like task allocation or flocking in a certain direction, what am I supposed to do? So we chat with each other and we say I want to go here, I want to go here.
Yeah.
Let's meet in the middle. Let's go that way. So that kind of averaging protocol would be an example of a distributed algorithm.
Gotcha.
Yeah.
That's pretty cool, but it's a lot of stuff at play to
Yep.
make things like, when you in your car driving, you hit cruise control and
Exactly.
it just does it. And
That's
there's so
right.
much that goes into
That's right.
getting that to work
Yep.
that way.
Yep.
Part of your research we talked a little bit about how information spreads through
Yeah.
the networks.
Yep.
So an example more of how that plays out in real life.
Yeah, absolutely. So, for example, when we think about something like an autonomous transportation system of the future, right? So we talked about robotic swarms and something like search and rescue. But if you think about autonomous cars becoming more and more prevalent, what's going to happen? They're going to be able to talk to each other as well.
Okay.
And so now you've got these autonomous vehicles going on these automated highways, right, which has sensors and communication infrastructure, everything like that. So now imagine that these cars can talk to each other and say, hey, I'm going to do this, or I want to merge into this lane. So that would allow the other cars to appropriately take actions so that
Okay.
they're not caught off guard, right?
Right.
Part of the big problem with the way humans drive is that other drivers do something, other drivers react to that. There's this kind of cascading effect that
Yeah.
goes on. But if I know that there's a car up front that's about to merge in and everybody has to slow down to let that thing come in, that requires communication to propagate through the system.
Gotcha.
And so then if vehicle infrastructure or the vehicles themselves could say, okay, you got to slow down, then everything can work together seamlessly. So that's an example.
So the instruction would be speed up real quick. That guy's going to merge. So
Right.
block him out.
Yeah, exactly. You would not, there's a lot of interesting things there. You could talk about adversarial behavior. That's why some of the security stuff that we work on is very important.
Yeah.
Yeah.
So a lot of what you do is find ways to stop either the misinformation or
Yeah.
malicious action from disrupting these networks.
Exactly.
How does that work in practice? How can you design a network to
Yeah.
protect itself
Yeah.
from bad things happening?
Yeah, excellent question. So, for the longest time, people were very focused on just making stuff work when everything did what it's supposed to do, because
Right.
that's a hard enough problem. But then it turns out you can come up with really cool distributed algorithms to make various networks function properly if everybody follows the rules. But it turns out that many of those algorithms are highly vulnerable to attacks. So networks are a double-edged sword. So essentially, it's useful to have networks because then people can coordinate, or nodes, agents can coordinate to fill in gaps in each other's information, right? It's like I'm
Right.
seeing this, or I have access to this information, you have access to that information. By combining our forces, we have more information and more powerful. So that's really important through these networks. But misinformation can flow just as easily as good information. So imagine, for example, a set of drones that are trying to do search and rescue, and they're saying, hey, does anybody see anything? Let us know so that we can go over there and rescue it. But then if one of those agents fails or is compromised by an adversary and they say, I see something way over there when there's clearly nothing going on there, everybody says, all right, let's go get
Right.
that person. And then they're like,
There's
well, there's
nothing
nothing there. So you can see how easily some of these distributed algorithms can be compromised by even a single adversarial node in the network. That's clearly not a good thing,
Right.
right? If you're going to be deploying this, you don't even have to have adversaries in the network. Things inherently fail in the real world, right? It's just the real world is complicated
Yeah.
and noisy. So then it becomes a question of designing algorithms to be resilient or robust up front. It's no longer a case of, oh, let's just patch it, let's just
Right.
throw a Band-Aid on there, because there will always be a way to get around the Band-Aid. So a lot of the work that we've done is trying to understand those fundamental limitations.
Mhm.
What are the ways in which the network has to look in order to be able to tolerate a certain kind of misbehavior or a certain amount of misbehavior? Part of that relates to how many ways are there for information to flow through the network. So coming back to this previous example, imagine we're in a big social network, right? Facebook or something.
Yep.
And imagine information has to get funneled through a single entity, a single person in Facebook to get to everybody else. If that single person decides they don't like the information coming from this side, they just change that information,
Right.
and everybody on this side of the network has no idea what was correct. They have
Yep.
no option but to trust that person. So if you are worried about the potential for certain actors or agents in these networks to be compromised or fail or spread misinformation, What you really need is for information to flow in multiple ways. You don't want single points of failure.
Right.
You want a lot of redundancy in the network and the way things pass. So then, in order to design these more robust networks, you have to make sure the network topology, this kind of network science aspect of it, satisfies certain conditions. You have to ensure that the resulting algorithms that are being deployed also leverages the diversity of information that comes out there, right? So it's like, this person said that person said that, this person said this.
Yeah.
So let me try and figure out what I think is real among all of these things. So that's how you would go about designing these networks.
So is part of what you do, I remember I talked to a professor who works in system verification, and
Yeah.
she said what she does is make systems not work to
Yes.
figure out how to get them to work. Is that what you do as well?
Exactly, yeah. So verification at the end of the day will be about making sure that something that's been designed already will do what it's supposed to do. Where we sit is more at the front end, which is how do we think about designing it up front so that it does what it's supposed to do. But of course, once you come up with those algorithms, you might program it incorrectly, even though the algorithm
Right.
you can prove on paper that it's correct. Somebody might have typed in a number wrong or an instruction wrong in the code. So then verification would be required to say, hey, look, this algorithm is supposed to do this.
Right.
Because it was designed that way, but it's not doing that. So in order to do that, the verification would have to try and break that algorithm. But similarly on our side, we think very carefully about the adversarial perspective, right?
Yeah.
So it's actually fun because you get to play both the bad guy and the
Right,
good guy.
yeah.
You come up with the thing and then you say, if I were the bad guy, how would I break this? And then once you figure out the bad guy strategy, as a good guy, you try and say, how do I make sure that can't happen?
Yeah.
And when you play that back and forth, you really get to get some good insights.
Yeah, like you said, I mean, the bad actors move as quickly, if not more quickly,
Oh, yeah.
than the good actors.
That's
so
right.
it's a constant process.
It is.
We talked a little bit about ways to stop misinformation
Yep.
or malicious actions. How does that work in practice? Like, we talked about a little bit how you protect yourself from bad actors, but misinformation is everywhere.
It's everywhere
these days. So how does what you do help prevent that?
Yeah, absolutely. So if you think about, so there's two different contexts, and I think, there's interesting insights in both. One is in the natural world, or let's say social systems,
Mm-hmm.
right? So when we think about misinformation, the natural thing to think about is something like a social network and misinformation flowing there. There, things are a lot more complicated because you can't really control people, right? And people will choose to consume what they want to consume. Maybe as a designer of the system, you can try and put in protocols to try and make sure people are better informed or able to make better decisions, right? And you've seen that with social networks,
Right.
which maybe does crowdsourcing to say this post is disputed or something, right?
Yeah.
So that's a minefield because it's very complicated and you have to model human behavior, sociology, and all that stuff, which we've worked on as well, but it's really complicated. In the engineering side, things are a lot, in some sense, easier because you get to program the nodes and you tell them, look, you're going to get a bunch of information, and here's how you take that information, and here's what you should do with that information.
Okay.
But if I walk up to a person and I say, you're going to get a bunch of information, here's what you should do, they're going to say, I'm going to do the opposite.
Right.
Because I'm...
Yes. Don't tell me what to do.
Exactly. Or they'll distrust you, right?
Yes.
Because they'll think you're trying to make them think something that they're not. So a lot of the work that we do focuses on the engineering context. And so, for example, we talked about this idea that you need multiple paths for information to flow. And so, as a very simple example, imagine you have a network, a sensor network, for example, and a sensor on this side of the network is gathering information and wants to transmit it to this other side. And if it has enough different ways for information to flow, you can imagine sending that information through the network. It's flowing through the network. Now, if only some of those paths are compromised by adversaries, the information that's going on the non-compromised paths, they're all going to agree with each other.
Yeah.
So a very simple kind of way to do this, a classical way to do this would be to say, wait till I get a bunch of information, then I just take the majority, I do a majority vote on that. I listen to what the majority of the paths are telling me, and as long as the bad guys haven't compromised the majority of the paths, I'm going to get the correct information.
Gotcha.
So that'd be a very simple way to do this, but they're much more sophisticated algorithms than that.
Gotcha. We're also looking at your research. You studied security and reliability of control systems in like power plants and transportation networks.
Yeah.
What makes these systems vulnerable? And I mean, it's probably obvious, but maybe people don't know why it's important to protect them.
Absolutely. Yeah, when you think about cybersecurity, right, often we think about cyber networks, right? Because in the name. And typically, for the longest time, the way we've thought about that is identity theft or some information being compromised, which is very bad and obviously causes, significant harm to economies and to people and so forth. What makes control systems different from that is that the control systems are controlling things in the physical world, right? So they're controlling the power plant, they're controlling cars. So now if people hack into the control systems, they can make those systems do bad things, which impact the physical world in a very negative way.
Yeah.
So we've seen this actually in several instances. So there was a very high-profile attack on the Iranian centrifuge system, the nuclear centrifuge system.
Yep.
So what was happening there is that there's a controller that basically controls how fast the centrifuge spins. That control system was hacked, and that caused the centrifuge system to spin out of control.
Okay.
Similarly, 2 years ago, there was in Ireland, water purification plants were compromised, so people lost power, lost water for a couple of days.
Okay.
The Ukrainian power grid was hacked in 2015, right? People lost power. So the big challenge and why this is important is because these systems interact with the physical world and they have the potential to cause physical damage. There's a great potential for attackers to really do really bad things. And so that's why it's important to protect them. What makes it interesting is that, a lot of these controllers are legacy, so they've been developed in the 50s and 60s because they didn't have to worry about this kind of stuff. And it's just like, okay, that's it, it's there. Then when the internet comes, some of these things are in remote places, so the natural thing to say is, oh, let's connect it to the internet, because then somebody who's sitting in a different city can monitor this remote place in Ireland and basically make sure everything's going okay. But again, a double-edged sword, right?
Yeah.
Yes, it allows somebody to monitor it remotely. It also allows a bad guy to basically compromise it through the internet.
Yeah.
So there's an increased sense of make sure critical infrastructure is not connected to the internet. But in other applications like robotic swarms and things like that, inherently there's going to be things that are deployed that you can't just have full control over, and some of these things might be compromised. Sensors will be compromised, etc. So that's where this notion of, try and prevent bad things from happening. You can't prevent all bad things from happening. So if an attacker still compromises your system, make sure your system has been designed to be resilient to that.
Gotcha. So your research affects everything, to small things maybe to very important things.
Absolutely.
When you're looking at students and students say they want to come do research, join your research group, what do you look for in a student that lets you know that they'll be successful?
Yeah, well, I always say to my students there's two things, right? You need talent and you need the passion. One without the other is not going to get you anywhere.
Right.
And so I look for that. So first of all, I look for interest, right? So the fact that the students are coming to me to work with me. So, at the graduate level, at the undergraduate level, we first try and identify what problems are of good interest to them. Because within this space, there's just a huge variety of different problems you can tackle. Some of them are application dependent, some of them are more on the theoretical side. So depending on the student's interests, we chat about that. And then, we start out with a simple problem that might be of interest to them, and then we get a sense for how they're tackling that problem. But in general, it's very important to have this kind of hunger to learn about these things, leverage the tools that are necessary and required, right? As you said, there's a lot of different aspects to these problems, so it requires a fairly broad base of knowledge. So I always tell my students, take as many courses as you can, right? Because sometimes students say, I can't wait to be done with courses, I don't want to take any more courses. But to me, I say, actually every course I've taken, I've learned something useful. It's a new tool. Yeah. It's a new angle to approach problems. And that's how you make progress, right? You come at it in a way that other people haven't. So I emphasize that. And then just this kind of sense of when you're doing research, really there has to be this sense of I am going to beat this problem. Right. This problem will not defeat me. Yes. I will come out on top. And having that sense of tenaciousness, which is to say, I'm not going to give up on this. Right. And that's what I think for graduate students sometimes is when they first start, the biggest difference between an undergraduate, experience and the graduate experience. Because in an undergraduate experience, if you're in a class and you have a homework problem, you don't know how to solve it, you'll say, I'm going to wait a week because the solutions are coming out. Right. For a graduate program, if you're doing research, nobody in the whole world knows the answer to this. Right. So if you don't solve this, unless somebody else picks up that problem. So it's not just let me just wait a week because the professor will tell me what to do. the professor's waiting for you.
Right, you tell me.
Exactly. So
I
look
mean,
for that.
we talk a lot about how failure is part of the process.
Absolutely.
And so, but for young people, that can be
Yeah.
really hard to deal with.
That's right.
How do you guide them through failure?
Yeah, we I tell them all the stories of my failures,
Mm-hmm.
And that helps. I think I always say, because one of the things, for example, when we do research is right, you pick a problem that you think is important. Then you do your literature review, right? Because you want to stand on the shoulders of giants and you don't want to reinvent the wheel. So
Right.
you try and understand what people know about that problem. And if you through your literature review you find that people haven't tackled that problem, that's an opportunity for you to fill that gap. And you might spend a lot of time filling that gap, and you might actually make progress after months and months of work. And then I always tell the story, when I was a grad student, I did that, and then I found an obscure paper from 1960 that solved this problem.
Oh, wow.
And so then you're like, I can't believe that, you
Yeah.
know? But on the other hand, it wasn't wasted effort.
Mhm.
There's an initial sting. But through the process of you filling that gap, you learn a lot about that problem. And after that first few days where you're a little bit dejected, you go back and say, wait a minute, that's very nice, but I was able to do it this different way.
Right.
And there's this additional insight. Or I'm so much better prepared now to take the next step because I myself solved this problem.
Right.
Or I can't believe I came up with the same solution as this really smart person did. So all of those are winning experiences.
Yeah.
So I think just framing it as it's not wasted effort.
Yep.
Any time spent in learning and getting a better appreciation is a solid win.
It's important as enough to find out what doesn't work as it is to find out what does work.
Absolutely.
So.
Absolutely.
Well, you work with students too as part of the Purdue AI racing team.
Yes.
So this is really cool. They're
Yes.
AI Indy cars that race around real tracks
Yep.
at like 150 miles and more.
Yep.
Talk to me a little bit about what the team does and
Yeah.
what your role is with the team.
Absolutely, yeah. So this is part of the Indy Autonomous Challenge, and so this is a competition that started, I think, 2020, 2021. So it's been running for a few years now. And the idea behind this challenge was really, take full-size Indy cars, just take the driver out, right? It's the same tracks.
No problem.
No problem, right? Same tracks, same speeds, So it's an incredible challenge. Why? So when you first think about this, you're like, well, there's autonomous cars, they're driving. What makes this different, right? And so what makes this different is that you really need to be operating at the very limits of performance in these vehicles. If you're not, then you're not going to win.
Right.
Whereas you very much hope that your autonomous car that you're driving in is not at the limits of performance, right? You
Right.
hope it's very far away from where it's about to spin out. So this fact that we have to push these vehicles as fast as they can to the point that they're almost skidding out
Yep.
and maintain the operation at that very limit is what makes this a very challenging and exciting problem. So there's lots of things there about modeling the car itself, right? So how do I know when the car is about to skid out? How do I know how much I can push it, how much extra acceleration I can add here before the car spins out? That's all part of this kind of what I started talking about in terms of control systems, right? That's the system. You have to understand the dynamics of that system and make it behave a certain way. So there's an incredible controls problem there. But it's not just about going fast, it's also about racing. So you have other cars on the track with you. So then you have to understand, using your onboard sensors, where those other cars are. So we have LiDAR, camera, radar on the car. So those are essentially the eyes of the car. So now you're looking at these, signals that are coming back, and some of it might be the stands, right? And some of it might be the wall, and some of it might be other stuff on the track. How do you know if that's a car or if that's that's just a sign?
Right.
And so you have to come up with these perception algorithms that'll take all of this data at incredible speeds, right? We're going at 150, 160 miles per hour. Huge amount of data, so there's a lot of, you don't want to spend a lot of time computing on all this data because there just isn't enough time.
Yeah.
So you got to do all that quickly. You have to make sure you're accurate. So you got to figure out where that other car is, what it's trying to do, with pretty good accuracy.
Yeah.
Because you're trying to overtake. And then once you figure that out, there's a whole planning piece, which is how am I going to overtake this other car?
Right.
And so then you have to anticipate what that car is doing. So you have to do behavior prediction. So is this car, just happily going on a certain path? Is it actively trying to block me?
Right.
Is it erratic?
Yeah.
Depending on some of the other teams, some teams are more aggressive than others. So if a team is just starting out, you can say that team is going to be pretty well behaved. It's going to stay as far away from other cars as it can
Right.
because it just wants to get around the track.
Yeah.
Whereas some of the more established aggressive teams are just, they're saying, I'm taking this track,
Yeah.
try and stop me. So if you kind of understand what the behavior is going to be, you can react appropriately and then plan around it. And there's a lot of risk with this, right? Because
Yeah.
there's the perception itself, your eyes are only so accurate on this car. So you can only say, hey, this car is within this region. I have a pretty good sense that it's here, but it could be somewhere within this bubble. So then there's a risk. If I try and execute an overtaking maneuver, I have to make sure I account for the possibility that that car is not exactly in there,
Yeah.
or that it's going to do something unusual. So when you put all of those things together, it's just an incredible challenge.
It's testing all of your
It's everything.
knowledge.
It's everything, yeah. And so it's there's nine international teams that participate in this from Italy, Germany, Korea, several from the United States, and then so there's a time trial version, which is just which car can get around the track as fast as possible. There's an overtaking competition, and now the competition is starting to think about multi-car, truly open, as you might see on a typical
Right.
human-driven competition. Yeah.
So is your team at banks of computers and
Yeah.
monitoring and making adjustments as the race is happening?
Yeah, you cannot make adjustments as the race is happening.
Okay.
You can only watch and bite your nails.
Right.
It's like sending your kid out and you're watching and
Yeah.
you hope it all goes well. And yeah, so the way the team is structured is it's a College of Engineering team. So we have 2 faculty from mechanical engineering and 2 faculty from electrical and computer
Okay.
engineering. So Professor Dan Williams for mechanical is the team principal, Professor Greg Shaver, myself, and Professor Steve France from ECE. So we're sort of the faculty advisors on the team. And then there's several graduate students, about 10 or 11 graduate students, both PhD and masters,
Yep.
split over these different roles of control, perception, planning, software, etc. We have several undergrads that are starting to help with the team.
Oh,
as
that's
well.
awesome.
Yeah, so it's a fantastic. It's really a student-focused team. It is a research enterprise. So it's not a hobby. It's
Right.
not it's not a student club,
Yeah.
for example, because this really is viewed by IAC and generally the research community is really an extreme opportunity to test systems at their limits.
And has the Purdue AI racing team's vehicle performed well?
Very well. So, the team's been around for a while, but really it's been over the past year and a half that there have been significant resources put into the team and by Dean Rahman from the College of Engineering. And so this sort of new team structure has had the opportunity to focus and really excel. And so in a very short time since the new team was constituted at the Indy Motor Speedway last September, we hit a team record top speed at about 140 miles per
Nice.
hour, which is fantastic.
Yeah.
And then within a short period of time, literally 3 months almost from scratch, we were able to put together an extremely good perception and overtaking solution. And so at the Consumer Electronics Show in January this year, we participated in the overtaking competition, and that's where we demonstrated fully autonomous overtaking of another car going at 130 miles per hour, we at 150 miles per hour. So just the team was over the moon.
Yeah. It seems like something that the people who are in it are really just way into it, very passionate about it.
It's hard not to be. I mean, you get to go to these racetracks and race cars for your job, and what kind of crazy job is that? I mean, so sometimes you just pinch yourself, and it's amazing.
That's awesome.
Yeah.
So when you're not teaching or doing research or on the track, what do you do to just relax or have fun or be away from?
Yeah. I have 2 kids, so they keep me busy.
Yeah.
So, we would definitely do all sorts of fun activities together. I'm a big movie fan, so I enjoy watching movies whenever I can.
Yeah.
Reading books is also a big thing. So, whenever I can squeeze in time to do that. And exercise is always definitely a good thing to do to, make sure getting the body moving and getting the blood flow to the head and all that.
Yeah. How old are your kids?
Oldest is 8, youngest is 5.
So do you see any kind of engineering leanings, or do their minds work in a way
definitely.
that you think?
Yeah, the 5-year-old is still up and coming. The 8-year-old, definitely you can see a lot of interesting things. One of the things about being a professor family, right? Both me and my wife, sometimes you have to bring the kids to work, right?
Right.
Because the school's out and we have classes to teach or something or meetings to do. So, I brought my son to some of the AI racing team meetings, and I'd just say, he'd just be coloring in the background. So he'd be sitting there absorbing, and, the students on the AI racing team are fantastic. It's just like a super talented group of students and just great kids and people overall. I shouldn't say kids. I get used to saying kids too. But they're awesome individuals. So they were joking with my son that he'd have to sit inside the car and throw banana peels out like in Mario Kart because he used to. So my son thought they were serious, and he said
he was pretty excited.
There's no room in the car for me to sit. But he, they're growing up really being exposed to all these different things, right? This idea of a car driving itself at those speeds. When I grew up, there was no notion of any such thing, right? And so for him, it's just this thing that people work on, and it works. So it's going to be quite incredible to see what they're able to achieve when they grow up. Even things like the internet, right? They're just able to understand that, hey, if I need information, I'm able to get it. And I think the school system is doing a really good job at trying to expose them to these things in a responsible way. And of course, first robotics and all these things, right? At the grade school level. So I think it's important that we continue to encourage those kinds of things.
Absolutely.
But I see a lot of potential in these kids.
I mean, you see, like, what 2-year-old today can't pick up their parent's phone and play a game or look at a video or something. So it's just, they don't even think of it.
Right.
It's just part of their lives.
That's right. That's right. And I have to be very careful that my kids don't see me typing in the password for my phone, because they will see it once and they will remember forever.
They're smart.
They're very smart and observant.
Yes, definitely.
Yeah.
So that's all for this episode of Engineering Innovations. We're the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'd like to thank our guest, Dr. Shreyas Sundaram, for sharing your incredible insights today. Thanks so much.
Thanks, Kristin. That's great.
And for more information about today's discussion or the latest news from Purdue ECE, you can explore other episodes. You can visit our website, purdue.edu/ECE. You can follow us on social media. We're on all the socials. So you can check the show notes for that information. Don't forget to like, subscribe, and share this episode with others. And be sure to join us again next month for another episode highlighting more groundbreaking research and innovation from Purdue ECE.